So today we're going to run some thin layer chromatography on our 6 standards, and we're going to make them up some ethyl acetate and hexane mixtures for the developing solvent. And we need to make a 1 to 9, 1 part ethyl acetate to 9 parts hexane, and we need to make a 2 to 8, 2 parts ethyl acetate to 8 parts hexane. The best thing to make those up in will be 10 milliliter graduated cylinders. And because I want to make sure I actually get exactly the right mixture, and I want to make sure I don't mix them up, I'm going to label a beaker with 1 to 9, and I'm going to label another beaker with 2 to 8, and these Sharpie markers write directly on the beaker. At least when the beakers are clean, they do. These beakers are apparently not very clean, so I'm going to have to resort to a label. So we're going to make our 2 to 8 mixture up in one beaker using one graduated cylinder. And we're going to make our 1 to 9 mixture up in another beaker using a different graduated cylinder. And then we're going to be transferring that into our TLC jars so we can run the solvent. And these TLC jars are in drawer A. They're sized to fit the TLC plate. And I'll be making enough solvent to fill 3 jars with about 1/3 of the solvent in each case. So I'm going to have my jars, and I'll also have them separated. So I've got 3 with the 1 to 9 mixture. Let's see if these are clean enough to actually write on. Nope. Either that or this is a bad pen. Try the other pen, see if the other pen is a little better. Yeah, there we go. So that'll be a 1 to 9 mixture. And in your notebook, you're going to write down not just 1 to 9, but 1 ethyl acetate to 9 hexane. Hexane is the nonpolar component of this mixture, and ethyl acetate is the polar component. And so by increasing the amount of polar component, we can cause the spots to all move a little bit faster. So I'm going to measure the ethyl acetate out first, since that's the smaller component of the mixture, by putting exactly 1 milliliter of ethyl acetate into my graduated cylinder. And then into the other graduated cylinder, I'm going to put exactly 2 milliliters of ethyl acetate. Now I can fill up to the 10 milliliter mark with the hexane. I've got the beaker there because this won't mix very well in the graduated cylinder. So I'm going to pour it into the beaker to mix it, and then from there transfer into the developing jars. Once you have it in the developing jar, it's important that the cap stay on there, because hexane boils at 69 degrees and ethyl acetate boils at 78 degrees, which means that the composition of the solvent will change, and gradually become more polar over time if you let some evaporate, since the nonpolar ethyl acetate, or sorry, the nonpolar hexane is going to dissolve fast or evaporate faster than the polar ethyl acetate. And it's important that we have the solvent mixture be the same for each of our trials so that our RF values don't move around from plate to plate. So we have our 1 to 9 mixture here. And since it's just volatile solvents, we don't really need to clean the graduated cylinders. We'll just set them in the back and let them evaporate. And the 2 to 8 mixture here. And we'll mix those thoroughly. And then we want to pour about 3 milliliters into each jar. Essentially, I'm just going to make sure that the same amount is in each of these jars. Not really going to measure it. It's not critical exactly how much is in there. I just want to fill them to about the same height. Three jars with a 1 to 9 mixture in it. And I'll have 3 jars with the 2 to 8. I'm going to leave those beakers and graduate cylinders in case I need to make some fresh solvent. They'll still be sitting there. So we have our developing chambers ready. So now I want to spot my standards on a TLC plate. This little crown here enables you to pull up the whole sample to more easily access the TLC plate. We want to be careful to handle them by the edges so that we don't get fingerprints. Fingerprints will stain, especially with the iodine stain, and we don't really want a big fingerprint in the middle. So we have 6 standards. I'm going to put 3 standards on each plate. Now I'm going to mark a line across with a pencil here. Definitely want to use a pencil, not a pen, because the ink in the pen will actually migrate. And actually I probably don't want this end to be the bottom because we've got some silica missing. It'd be better to use the end that doesn't have that silica missing, or it'll develop a little crooked. And I'm just going to put kind of an X. It'll tell me about where I want to put my spot. And then I'm going to label them. So on this plate I'm going to be putting linalool. So I'm going to label that with an L. And then I'm going to be putting the 2-phenyl ethanol. I'm going to call that PE. And then the phenethyl acetate, which I'm going to call PA. And on this plate I'm going to be putting guaiacol with a G, and eugenol with an E, and vanillin with a V. So I'll know what I'm putting on each plate. It's important that the line you draw is above where the plate's going to sit, because if the solvent goes over the top of the line, you're going to dissolve all your spots into the solvent, and then it'll all go up in one big smear. So it's not really critical exactly where that line is, just that it's above the solvent. With the exception of linalool, all of these spots, or all of these compounds rather, have an aromatic ring in them, which means that they will absorb UV light. the plate is silica gel, which is basically a highly refined sand, silicon dioxide, SiO2. But since silica will not stick to this plastic backing, there's a gypsum binder, calcium sulfate binder. We have the silica gel suspended in the gypsum binder, and then we also have a fluorescent indicator. And what that fluorescent indicator will do is cause the entire plate to glow white, right? So you can look at that and you can see that the entire plate is kind of glowing white. If the compound that we're spotting on there absorbs ultraviolet radiation, it will absorb the ultraviolet radiation and prevent the fluorescent indicator from absorbing it. And what we'll see is a dark spot where the fluorescence is quenched. Right? Silicon dioxide is a network covalent solid of silicon and oxygen atoms, but at the surface, they are capped off with hydrogen. So at the surface, we have a silicon with an OH group. So it's a very polar stationary phase with hydrogen bonding capability both as a donor from the hydroxyl group and as an acceptor for the lone pair on the oxygen. So things that are capable of hydrogen bonding that have hydrogen attached to nitrogen, oxygen, or fluorine, but obviously we're not going to work with HF. HF in fact dissolves silica. Those will stick tightly as hydrogen bond donors, and then hydrogen bond acceptors, molecules that have a lot of oxygen in them, or carbonyl groups, or nitrogen lone pairs, those will also bind as hydrogen bond acceptors. So we would expect that the more hydrogen bond donor and acceptor regions on the molecule, the more tightly it will bind to the stationary phase, and therefore spend less time in the mobile phase, which is either the ethyl acetate or hexane, or the mixture in this case. And the amount of motion will be decreased, and the ratio to the front, the amount the spot moves versus how far the solvent front moves, will be smaller, have a lower RF value. RF stands for ratio to the front. And we measure the RF by dividing the distance the spot moved by the distance that the solvent front moves. So it's always a number between 0, which is no movement at all, to 1, which is going all the way to the solvent front. Right? It should be a decimal, and we usually use 2 decimal places for our RF values. So I'm going to start on the right here with the vanillin. We've got our TLC spotters. These are pipettes, capillary pipettes, just like this, that have been heated in a flame until they get really mushy and then drawn out to give a much finer capillary. So if I dip this into my compound, by capillary action, the compound will go up the plate, or up the spotter, and then when I touch it to the plate, I can get it to come back out. It's important that it be flat on the end, so I kind of tweak it with my finger until it looks like I've got about a flat end. And then these can be reused. I just need to keep track of how far up into the plate or into the capillary the sample went, so that I can break off the capillary above that and make sure I don't get cross-contamination. So I've got up to there. So I will be breaking this off just about where my finger is. And if I want to see how much I'm spotting, I can turn on the UV lamp, and I can kind of watch what happens as I tap that on there. I should be able to see a dark spot, right, where the compound has come out. And that's a good size spot, maybe 2 to 3 millimeters in diameter, something like that. And then I'm just going to break off that little piece, which was contaminated with the vanillin. And usually I just dump it on the floor, but in this case I'll put it in the glass waste. And now I can move on to the eugenol. So you don't really need very much. We just need to dip that in there until it comes up into the capillary enough to get some spotted on the plate. Right, so it's up to there. I move my fingers down to about where it was. That'll tell me where to break it off. And then I'll touch it to the plate until I get a nice size spot again. And then break that off. And finally I'm going to put the guaiacol Right, so you can see that I didn't stick that in there for very long, just a quick dip, so that I don't waste a lot of the spotter. And this works as long as the compound is UV active. Obviously, if the compound's not UV active, then you can't see it under the UV light. So I've got my plate, and I have my vanillin, my eugenol, and my guaiacol. If you can't see the spots clearly at the baseline, you won't be able to see them once they develop either. So it's always worth looking at it under the UV light to make sure that things are good. So I'm going to move that plate over here. And now I'm going to spot the other three compounds. The 2-phenethyl acetate, I should be able to use this one spotter for all of my samples. And some of these will be more UV active than others. And the linalool, since it does not have an aromatic ring, won't show up under UV light. So that one I'm just going to have to spot about the same amount as I've spotted on the others, and trust that when I do the staining it will show up. So then there's the 2-phenyl ethanol, or the phenethyl alcohol. And finally the linalool. Sometimes there are small impurities, and you can often see a little bit of kind of where the liquid is still there before it evaporates, so you can kind of get a sense for how big a spot you're making, even though it's not UV active. Right? So I think you can see that there's kind of an edge around there that